My name's Bob Amar. I'm an independent school teacher in Atlanta, Georgia, and we are heading into the last few streams here, leading up to the AP Stat exam. So today we're going to be talking about collecting data. We're going to be talking about sampling, surveys, experiments, all that stuff, all in the context of different FRQs and portions of FRQs that revolve around it. It used to be that in AP statistics, you saw a lot of just questions that were design an experiment or do a survey. And those questions now, those concepts tend to be wrapped now into different FRQs. And they are portions of questions now. So we will not do all of every FRQ that we see. We're just going to do the part that involves collecting data. But this topic is a big one. It has its tendrils out into a lot of different things. And so we're looking to get a real good understanding of what it is that we're doing with all of this. All right. Give us a follow, subscribe. I think we have a TikTok now. That's what I've heard. So look for that. We've also, we've got a Discord too as well. There's a server for I think for, I don't know if it's just Cram Pass, but there's a Discord server as well. So, all right, so this is what we're going to talk about today. This is quite a dense topic. So I'm going to try to break it up as much as possible. The slides should give you kind of a guide as to what the major concepts are. And I'm going to show you how these things arise in the context of different FRQs. So let's go ahead and let's get this started. We're going to go just beginning. What are the types of studies? And then we're going to ramp up and head towards blocking and matched pairs and sophisticated designs as much as we can get done in this hour. Okay. Some dense text here. I'm going to give you a chance to process it, but I like to just put everything we're talking about in one place, so you can refer to it later more than anything else. The main thing that you need to know is the difference between an observational study or survey and an experiment. In an observational study, you're not affecting the behavior of anything. You're just seeing what happens out in the wild. You're measuring one or more variables. A survey is much the same, except you're actually asking people or what they think or what their response would be to a particular topic. And when you do that, how you ask the question matters. And so the wording of the question matters, how you ask the question matters, and that is a level of influence that you might have on the measurement. Okay. But in general, when you're looking at an observational study or a survey, the key unit there, the group that you're studying from is called the sample. Okay, so you are collecting a sample, you're getting a sample, hopefully from that's representative of the population that you wish to study. Samples are random samples are always representative of what we call their sampling frame. Hopefully the people that you are sampling from, that includes the whole population, but you might run into some cases where you can't reach everybody. You also want to be familiar with two different kinds of observational studies. This is more of an emphasis this year, I think. Retrospective observational studies versus prospective. In a prospective observational study, you're basically selecting people and following them as they go, versus a retrospective study where you're collecting data that has happened to these subjects in the past. When you have more than one variable that's being measured in a survey or observational study, you can establish an association between two variables. You cannot establish cause and effect in general from one observational study. There are processes that some books talk about for how you can establish cause and effect. Cause is a super important word. Cause is a word that if you look at it as you're reading an FRQ, you might skip over it and think, oh, well, okay, you might mistake cause for association. But those two things are not the same. It's very important that you keep that distinction in mind. Okay. Now, the other kind of major data gathering arm or process that we use in AP statistics is called the experiment. In an experiment, you assign groups to treatments that you specifically manipulate, and then you measure what they do in response. If you have designed this experiment properly, and some of those principles are, well, I don't have like a list of them in the slide deck, but we are going to talk about quite a few of them: control, replication, randomization when necessary. All of those things are super important when designing a study. And then random assignment is the linchpin that pulls all that together. Okay, let's kick it off with an FRQ. Okay, so this is a question that is it's a pretty common question. Actually, you're going to see this now more and more on the SAT as well. Looking at the STEM, the stimulus for the problem, it talks about researchers determining whether drivers are significantly more distracted while driving when using a cell phone than when talking to a passenger in the car. Okay, so you can read all of these different aspects. It's boring if I read them to you, but there's lots of different words here that are important. But the data is given to you in this form. The data is not given to you in a table. The data is not given to you in a set of summary statistics. So you kind of have to pull out the important parts for yourself. So the first question that's asked, that's germane to what we just talked about, is this an experiment or an observational study? Provide an explanation to support your answer. Okay. So let's think about that for a few seconds, and then I would just love for you to just hang on a few seconds, and then I want to see some. Good. We'll try it. I actually want to try this. I've never. Good. So I see a couple of explanations in the chat. So everyone's going with experiment, and you were correct in this case. This is an experiment because, and then we need the explanation. So if we go back, the main thing that sets an experiment apart from an observational study is that you are manipulating something and then checking the response. You are assigning people to treatments. Okay, and that's what makes this an experiment instead of an observational study. Now, this whole format with the new format, I'm not sure how much they're going to really get into the vocab this year, but you should be able to answer some other questions about this. Like, for example, what are the experimental units? Identify any explanatory and response variables. Okay. Let's actually go ahead and let's just take these things one at a time. I've added these. They're not in the original thing, but I just want to make sure that we talk about these things. So the experimental units are those things for which you are measuring a variable. Okay. So you need to be aware of whether, I think the biggest distinction you need to make is, for example, are the experimental units the individuals that are being tested, or it could be that they are containers or groups of people, and so you need to be careful like that. There's I don't know if it's in this slide deck later, but there's a really good example of a recent FRQ where they basically asked, do you like if you spray plants, or if you spray with a fungus, how many insects would it kill? And what they did is they put insects in containers, and then they sprayed inside the containers, and they see how many insects are still alive. The insects are not the experimental units in that case, because you're not measuring the dependent or response variable at that level. But in this case, we are checking to see, for example, and you can see it says 7 of the 24 cell phone users missed the exit. So in this case, the experimental units are in fact the users, because what we're doing is we're measuring whether they missed the exit or not. The proportion is the sum total, but the response variable is, did they miss the exit? And so the experimental unit here is are the people. Explanatory variables, the kind of distraction. So when I'm asking you for the explanatory variable versus the treatment, the explanatory variable in this case is the overall category or the thing that's being measured, whereas the treatments would be the individual types of distractions. So a passenger in the car versus a cell phone. Okay. I won't make a poll for this, but is this experiment blind? Okay. This experiment is almost certainly not blind, because it's like you'd know whether you were you had a cell phone as a distraction or whether you had a person in the car with you. You'd know what treatment you were undergoing. The main reason that you would need to blind involves a lot of it involves the placebo effect. So for example, if your control group doesn't receive any medicine at all versus giving them some medicine, it's important, even if that medicine is just a placebo or a sugar pill, it's important because just receiving a medicine makes some people think that they're getting better. is there a control group in this experiment? The answer to this question is also no. Kate's got it. Yep. And the control group would be a treatment that has there's like a treatment with like no distraction. You would just see how many people you would just miss the exit in general. And so this experiment doesn't have a control group. You won't be able to compare it to a baseline, but you will be able to compare the types of distractions to each other. Okay, so that is concept number one in our sort of our kind of blitz through collecting data here. When you collect a sample, or when you construct a sample from which you are going to do a survey or an observational study, there are several different kinds of samples that you can use. The gold standard one, the one that all of our techniques that we've derived in this class are based on, that's the simple random sample. The simple random sample I equate to names out of a hat. So in a simple random sample, there's a more technical definition that means every possible sample has an equal chance of being selected. That's what you get with names out of a hat. You need to make sure that if you're putting names out of a hat, that you shake the names that you put in there well, or else you haven't fully randomized, right? If you just put them in alphabetical order, like if you write them all down in alphabetical order, you throw them in the hat and then you don't shake the hat, it might be more likely that you'll pull some of the things you put in last. For example, other kinds include the two that are in the corners there, the stratified and the cluster sample. Those are often asked about on the AP Stat exam. In a stratified sample, both of them involve creating groups. In a stratified sample, you're taking a little bit out of every group. Okay, so if you think about a sample, like you're sampling from a cake, for example, a stratified sample means you take a little bit out of every layer of the cake, which is not normally the way you eat cake. You normally eat cake in a cluster sample where you're just going to take a slice out of the whole thing, right? And so in a cluster sample, you take one or more groups out of the whole with the hope that each group is representative. In a stratified sample, you're making sure that out of each of the groups that you create, that you get a few out of every group. And these are best when, if you actually happen to know how much each group makes up of the population, that the sizes that you pick out of each are proportional. Finally, there's this thing called the systematic sample, which means you choose every nth, like every 5th, 10th, 4th, 8th, whatever. In order for it to be truly random, you have to randomize when you start collecting data. So with those sampling techniques in mind, let's look at this joyous FRQ. I feel like I'm pulling these. I've actually tried to pull these from the more distant past, because I just finished doing 3 streams in which I did the 2017, 2018, and 2019 FRQs. I didn't want to just repeat myself. So that's why I've gone back to some of the older FRQs. Of course, we run the risk in that case that I'm pulling things that you've used in class. Hopefully I'm not. But if you are, it's kind of if you have seen these before, it's a good review. I also like just to break these down. So there's actually a diagram provided, and when we look at the 2 prompts, we'll talk about what we're actually. Okay, so what I want to do is actually type out the sampling method. The important thing that you have to do is describe a process that's bare bones. So you're not spending a lot of time, but you are describing all the things that are important. Because if you don't do that, then you're going to run into some problems in terms of the score you get for the question. Okay, so the important thing here is that the floors are clusters. If you do anything that doesn't honor that clustering scheme, you wouldn't get full credit for this. And so basically, the groups are floors. So I need to pick enough floors to satisfy the requirements here. And I'd like to select 8 apartments. And because there are 4 floors per apartment, I need to select 2 floors. So let's make a little room. Okay. In part A, what we're doing here is we need to select 2 floors at random. Okay. So once we know that we need to select 2 floors at random, there are 9 floors to choose from. So we can just use the processes, hopefully, that we've internalized to describe an effective way of selecting the apartments. Okay. So what I'll do, there are 2 different versions of this. One version is to just say, write the numbers 1 through 9 on slips of paper. Put them in a hat. Mix the slips well. You need to include that. Draw 2 of the slips. The apartments on the floor corresponding to the numbers drawn will be the sample. Okay. Now, that to me is like the bare minimum description. Okay. Because what you're doing is the following. You are describing a process that labels each of the possible choices. You're ensuring that this is going to be a random sample, a simple random sample of floors. Okay, and so what this process will do is then also this description differentiates between the numbers that you've used and the actual apartments that are in the sample. Because if you just say if you said draw 2 of the slips, that's the sample, that you're not being specific enough, and you wouldn't get full credit for that. Okay, so the cluster sample consists of the 8 apartments on those 2 floors that are drawn. Okay. Part B. An alternative sampling method would be to select a stratified random sample. Oh, this is good now. Okay. Now the strata are told to you here. Apartments with children and apartments with no children. And now what you want to do is make sure that you select enough out of each of the 2 groups, right? And so let's take a look at it's actually described for you, but I just want to show you what I mean by proportionality here. Let's count the number of asterisks here. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 apartments, okay, that have children. Okay. Oh, it actually says that in the problem stem too, but you can count. Okay, that's 9 out of 36, right? So that means that 1/4 of my sample ought to be apartments with children. Then the other 3/4 ought not to be, right? And so you can see in part B, that's what they've done. 2 randomly selected apartments with children, 6 without. Okay, and that preserves the proportion. Okay, so now thankfully we're not asked to do this. Although I would just write the numbers of the 9 apartments with children. And then select 2 of those, and then put in one hat, mix them well, select 2 of those, then put the other slips of paper in another hat, mix that well, draw 6 out of there. Okay, and that's your sample. This is what is a statistical advantage. Okay, now this is a very important thing that we'll come back to later. There has to be an advantage in order for you to go to this trouble. Okay, when you stratify, you believe that there is something going on that will be between the strata that will affect the response. Okay, so you need to say what that is, or there's no reason for us to be doing a stratified sample. So it is plausible. That's probably that carpet will wear differently in an apartment with children than in one without children. Okay. So using a stratified sample ensures that you will have both groups, both kinds of apartments, I should say, represented in the frequency they occur in the building. Okay. This would ensure that the sample data truly reflect both types of apartments. That was the bare minimum, essentially the bare minimum response. One aspect here that's important as well is that such an approach in general also limits the variability of the response. The variability in the where measured would be lowered if there truly is a difference between the two in an apartment with children, one without. This is an important thing that we'll get back to. If you can do something to make sure that you steer your sample or response towards, and it's slightly different for sampling than it is for blocking. Okay, in an experiment, it will get rid of some of the measurements. Like you have some samples that will consist only of apartments without children. Those might show a lower wear. You have some samples that consist entirely of apartments with children. Those would show a higher wear than normal. This gets rid of those extremes. Okay, and it's an advantage of a stratified sample over a simple random or a cluster sample. Okay, let me just pause and see if anybody has any questions. All right, I am trying to make sure that I give you time to read, but not to sit there and just have you read. You can look up obviously these questions and their answers as well, but I like to just take a moment to. Okay. Another class of questions that are asked about data gathering procedures on a free response is, what can we generalize to? Okay, what kinds of conclusions can we draw? And it's important to be able to have a way of doing this. Your book. If you're using a textbook, like most common textbooks tend to have nice little 2x2s that say, like, is it a random sample? Yes, no, then you can generalize. But this is kind of how I think about it. The results of a study can only be generalized to the groups that the sample that you've picked or the people in the study represent. Okay. If you are dealing with a random sample from a group, the results apply to then that random sample is believed to be a good representation of the group. Okay, and so we would trust that this result would generalize to the entire group from which it was sampled. But that has to the key word there is random. Okay, and usually we say simple random, and that's how all of the math that we're doing, all of the formulas like the root p hat times 1 minus p hat over n, all of that stuff depends on a simple random sample. You can develop more sophisticated measurements, but they're not covered in this course unless you're doing a question 6, which we're not doing this year. Okay. Now, if you randomly assign to treatments, then you can assume, and this experiment's well designed, then any significant difference is attributable to the difference in the treatments alone. That's a cause and effect relationship. That word cause is so important, and you don't overlook it when you're reading problem stems or when you're reading questions. Don't miss that word. It's a very easy word to miss. You don't mistake it for association. Cause is a very specific thing. Okay, so let's take a look at a couple of different things here. This is a lovely back-to-back stem plot. That could be its own stream. Reading stem plots, reading kinds of different graphs and what they show you. That is not the point of this stream. I'm going to assume that you could write a proper comparative study for the urban and rural populations. I'm only interested in part B. Okay, so the question is it reasonable to generalize the findings to all? Okay, so lots of no's. That's good. Because remember, just the general principle is that if I'm doing a study, I can only generalize it to students from like that. I can only generalize it to people that are like those like those in the study. And in this case, there is a random sample. Okay. In this case, there is a random sample, but what is it a random sample of? What was the sampling frame in this case? Yes, the sampling frame in this case is where we took the samples from. So these results could be generalized to every ninth grader in those schools, but could not be generalized to other ninth graders. The thing about this question, honestly, is that the word is not bolded, it's not underlined, it's not highlighted, it's not like, hey, I'm asking you about cause and effect, right? It's that one little word in there with a whole bunch of other words and a whole bunch of symbols. It's easy to miss. Okay, so that's my diatribe about cause and effect questions, is that it's easy to miss that that's actually what you're being asked to decide. We go. The answer will not always be no to these questions that I ask, but it is no again in this case. It can only be generalized to people like the ones in the study. Okay, and so yes, they did a random sample of 28 men. So these results could be representative of everybody in the community, but the question is asking about whether daily meditation causes a reduction in blood pressure. And the question is, were people randomly assigned to meditate? And so in this case, the reason that you could generalize to some degree to the whole group, but you can't actually establish cause and effect in this case, because you did not make people meditate or not meditate. Okay, and when you fail to control for that, then what's introduced is something called confounding. And Fatima's got the right idea there. Let's take a little sneak preview into. There's a discussion of confounding coming up a little bit. What are some of those things that might be confounding? What's your current understanding of when I say like what could be a confounding factor, right? So the factor that you hope is causing this is meditation versus not meditation. Okay, what factor could be confounded with meditation? All right, the key here is that there are two things that always go into exactly what you have to establish there is that there is some other thing that might explain the response, and that thing that explains the response could be mistaken for the other factor. Okay, so things like look at the explanation that Kate put down is pretty good, right? So if you have people, the kinds of people who like to meditate might also engage in healthier lifestyle choices in general. And so you have to mention that those things are linked. And when you have that, you've got it. Okay, so that's the important thing about confounding. They're like it literally means poured together from the it's Latin. Is it Latin? Confounding. They're basically they've come together, and you can no longer tell once you've poured those two things together which of them is causing the thing that you're observing. All right, excellent. Good. I'm in the wrong window. That's why that didn't work. Okay, so now we're going to talk about two of the very most common problems in data collection. Okay, these aren't necessarily constrained to one thing, one kind of study or the other. In general, bias is a thing we tend to ask about related to a survey or an observational study, but more likely a survey. Whereas confounding is something that tends to occur when we talk about experiments or or in some cases, observational studies. Okay, so here's the thing, and this is my, if you watch one of my streams before, then you know that I'm on this kind of like soapbox about bias. And it's not because I'm like super good at explaining bias and keeping my students from doing it. It's because my students misexplain bias all the time that I'm kind of like, it's almost like I'm mad at myself for making sure I want to make sure that you don't fall into the same trap. Okay. And so bias is not just a catch-all term that's like, oh, my study's biased because it's not designed right. Right? You got to be specific. A bias causes you to miss the target. Right? Some of your textbooks have like the archery analogy for bias. It's like all like the arrows are all clustered together, but they're all wrong. Bias is whether or not you tend to be right on average. And if you have a low-powered design, it could be unbiased. It's just gonna have a lot of variability, and you might not always measure the thing that you want. But bias means you're gonna systematically do it wrong. Okay, so these are caused by a variety of factors. If you sample poorly, then that's going to cause you to miss the target. It's going to cause you to measure something that isn't the thing you're intending to measure. So undercoverage is, in particular, I like to list here, like when your sampling frame is not as big as your intended population. The classic example is the phone book, right? Another example that's shown up on recent free response questions is when you want to estimate the median price of an apartment in a city, but you only go to this one website. That's undercoverage, because if you just look at the prices that are on that website, it doesn't necessarily tell you all the prices that are out there to be found. Like maybe people who can't afford to list, or people who aren't sophisticated enough to list on that website, or the website itself could be exerting some kind of selection on those prices. So undercoverage is a pretty important thing to know, right? And that's sometimes it's hard to predict what the effect will be. For one thing that's pretty well established is, in general, if you just voluntary response. Also, people mix up voluntary response and non-response, but let's just go through that. So voluntary response is when you just put your survey out there and just let anybody take it. You don't even exert any control over the sample. Most people just who feel strongly one way or the other generally respond to those. Often, if you just people like to complain, and so they tend to skew negative as well. That's a thing that's plausible. But that's the main problem with that. Convenient samples as well. You're just measuring something that doesn't represent probably the whole population that you want to study. Okay, so voluntary response is different than non-response. Most people call non-response most people call non-response voluntary response, right? You only have people that want to respond. Non-response is just a different kind of thing where in non-response, you carefully selected your sample, they just didn't come through. And that will still cause a lot of the same problems as voluntary response, but non-response is just a different animal. Okay. Non-response can be combated by to a degree by providing incentives and whatnot, and just having ways of making sure that people respond. Response bias is a particular kind of thing where the behavior of the interviewer in a survey establishes some kind of dynamic that causes a person to respond in a way that different than they normally would. That's response bias. Okay, so you have to be able to explain what specifically is causing the estimate to be wrong. And then, if possible, some questions ask you to estimate what that effect would be. So, for example, if a police officer were to survey a random sample of students in a school, a police officer in uniform, about whether they speed or not, more people are likely to say no, even when they normally would have said yes, because a police officer in uniform is asking them. Okay. So let's take a look at some things. Let's take a look at some issues here. Okay, so we're actually gonna do now. I think we only do part A of this one. All right. So an administrator at a large university wants to estimate the proportion of students who are satisfied with the appearance. Okay, so sometimes like that just the thing that you're reading you might need to go through the whole course before you come back to this and really go, oh, wait a minute, right? The administrator is measuring p hat, right? And the administrator would like to know whether their p hat is a good p hat. Okay. And so then when you realize that, okay, well, I know how to run p hat through its paces now because I know how to conduct a one proportion z-test now. And coming back to this is often like it can provide some more insight. So I'm hoping that if you've not thought about that, and then it kind of gives you some food for thought there. All right, so the first thing is a convenience sample to keep the expenses low. So part A is all we're going to do. So the administrator is thinking of just doing a convenience sample of the first 500 students who enter the football stadium. Why might such a sampling method be biased in producing an estimate of the proportion of students who are satisfied with the appearance of the buildings and grounds? Okay. So when we answer this question, we need to ask, what kind of estimate would we get from this that would be different than sampling randomly from the whole university, 500 students? Okay. So when we answer this question, we need to make sure that we do a few things. Okay. I'm hoping you guys are all familiar with the scoring system in AP Stat free response here, by the way. My belief is that they're still going to use it. And every portion of a free response question is given a grade of E for essentially correct. Even if you've made a small mistake in the math, if your explanation and your statistics is essentially correct, you get an E. That's full credit. P is partial or partially correct, and I is incorrect. Okay, so generally, for a question, it's graded out of 4, and there'll either be 3 or 4 E's, P's, and I's. And so what we're looking at in part A is essentially a rubric for what's necessary to get an E. And the fewer things you include in that rubric, the lower your score gets. Okay, so there are 3 things that have to occur here. First, you have to show that you're going to measure the wrong thing, and that's the reason we have the bias in this case, is that the thing that we are measuring it's not a good way of measuring the thing we intended to measure, because this group is not representative of the whole. Okay, and so then there is some kind of link between the fact that it doesn't represent that and what effect it would have on the variable of interest, and then finally what direction the bias would go in. So I want to change the dynamic here. I actually want to show you a sample student response. And then I want to ask you whether it has all 3 of these components. So again, provides a reasonable explanation for why the sample is why it's not representative, the fact that this non-representative nature will have something to do with the variable of interest, and what the direction of that would be. I'm going to give you a second. I'm going to ask you to just, I'm just going to ask the question, would this have gotten all the points? Okay. A better question that I will put in the poll is, would you grade this an E, a P, or an I? Okay. You'd grade it an E if it shows all 3 things. You'd grade it a P if it only shows 2. You would grade it an I if it shows 1 or fewer. And I'm going to put it in the chat, a summary of the 3 things. Okay. See a couple votes for P. I know people do tend to, I see people are voting eventually, which is great. You can keep engaging with this question. There's lots of support for P. And in the case of P, which is how the readers for this question did grade this response, which of these 3 things is not included? This is basically about closing the loop. The student has identified the central drama in the problem with the convenience sample, but has not tied it back to to the estimate that the administrator is actually trying to collect. And like you'll hear me, like if you've watched any of my streams, you know that I get a little bit. There's some things that the AP Stat folks expect you to say that they don't explicitly tell you that you have to say. Like they don't walk you through every part. But in terms of statistical practice in this case, what the student has not established is why this is not going, how this is going to show up in the proportion that the administrator estimates, and why that proportion would actually then be wrong. Okay, these students will not likely have a problem with their school's appearance, but that might not be what happens for everybody. And so element 3 here is missing. This is likely to produce an overestimate of people who are satisfied with the school's building and grounds. All right, I do want to make sure we end around 5 today, just to be, I'm okay with going a little over, but I know like some of y'all might have places to be. So a school board is going to conduct a survey of parents' opinions. This is a great question. I really like this question. I really encourage you to look it up. But what's happening here is that they sent a survey to 500 families and only 98 families responded. And the question is, what is a possible consequence of non-response bias for this in this case? This is kind of important. Okay. So when I look at this again, I want to put this in the context of what we're doing. Okay. These 98 families that did respond would have to be would have to represent the group well. If there's something about these 98 that were more likely, there's something about them that makes them more likely to respond, and how would they support the initiative differently. Okay, so an answer to this question then, a possible consequence might be something like the following. Okay, you would need to actually say something like what would happen. It's a possible consequence. You're being asked to estimate. Okay, these people might support year-round schools more strongly. If the 402 families that did not respond to the survey are less supportive of year-round school, which is possible since people who respond tend to feel strongly about an issue, and this would result in an overestimate of the true level of support for year-round school. These 98 families may not be representative of the district as a whole. And so the conditions here are linking the response to some directional bias. Okay, so you would get a P if you describe a reasonable consequence or an issue related to families who are likely to respond or not to respond, but not if you linked it. You did have to go all the way with bias on this. So this is a very important distinction that we're making here. Oh man, I just realized I don't want to run over the opening ceremonies here. So let's do confounding real quick. There we go. Okay. Again, we talked about confounding a little bit, but again, it's where the effects of two factors on the response can't be separated. This happens a lot if you're doing this. This is pretty much the story with an observational study. You're not actually controlling anything. So you can't tell whether it's the variables that you controlled that would also be associated with the different categories or groups that you put them in, or the different response that you measured. Another thing that can happen is the placebo effect. That's often why you blind, especially in drug tests or something where it's important that like, for example, it's important. Some people said it's important that you spray every tank in the fungus killing insects question, even if the thing you spray has no fungus in it, so that every condition is the same, because maybe it's the water that kills the insects and not the fungus. And finally, failing to include every possible combination of factors as a treatment. Yeah, so that's a very important. Those things are things that happen with confounding and situations in which they arise. Okay, we've talked about a little bit about confounding already, but I'll just walk us through this real quick so you can read the prompt. And the question here is, in part B, is explain the concept of confounding in the context of this study. Okay, so the confounding in an explanation says we need to be able to clearly identify the response variable and an intended explanatory. So the intended response variable appears to be the number of new cavities in the two groups. Okay, the dentists are measuring the number of new cavities in the two groups. They want to establish a link between apples, the eating of apples, and the number of new cavities. So routinely an apple a day, and then versus less than that. Okay, so that's two groups, and they want to show that the groups are that there's probably a lower incidence of cavities, or that there's at least a different incidence of cavities. Okay, but confounding says that there is something else about people who eat apples regularly that would then contribute to them to having fewer cavities. And again, often it's a lifestyle hypothesis. So people who eat an apple a day likely also have other healthy habits that would affect the number of cavities that they would have. If you're not controlling everything else, then you can't separate out the effect of the apples. Okay, and so that's what's happening in confounding. And when you have confounding, if you were to go to part C, you could not establish a cause and effect relationship. Okay, this is the last example that I have. It's about stratified sampling and matched pairs and blocking. Okay, we talked a little bit about stratified sampling in the apartments question, but now I want to talk a little bit about blocking and matched pairs. So you may have seen, this is another thing you may have seen, instead of just taking all your people and just assigning them to treatments, you might take the people and specifically separate them by some trait that they have that you think makes them respond differently. So for example, if you're testing the effect of a drug, I feel like I should have more imagination about this, but if you're testing the effect of a drug and what you're doing is you think people who have like high cholesterol or have obesity or some other health factor would respond differently to the drug, or these people are sensitive to some component in the drug, you might separate them. Well, if they're sensitive, you probably wouldn't put them in the study at all. But if you think that is true, you want to measure their responses separately and before combining the results. Okay? And so measuring them separately, often in blocking, what happens is that what you're actually doing is just isolating. You're just isolating you're removing one variable entirely from your response. That's what causes the variability in that to measure, to reduce. So like if a drug produces a stronger response in people who have high cholesterol, then simply looking at a group of people who have high cholesterol will lower the variability that you see. Okay. We already did stratification, so I'm just going to skip to this because this is a classic example of matched pairs. If what you did was simply take the 100 volunteers and give half of them boots with the new waterproofing and half of them boots with the current waterproofing, and you just compared the two groups of 50 volunteers, then you didn't get full credit for the experiment. Okay. A better, more sophisticated way to design this experiment would be to take all 100 volunteers and then give them let them do both things, and then run what's called a paired t-test just on the results you get from the 100 volunteers. Okay, So a design for this experiment could be something like for the 50 people, like randomly give 50 people the old method and the other 50 people the new method for 3 months, and then have them switch. Okay, so you take their boots back, and then you give new boots to those 50 people in each group. So one group of 50 would get the new method for 3 months, and then the old method for 3 months, and then the other 50 would get the old for 3 months, and then the new for 3 months. Okay, and then what would happen is you would measure the difference between new and old between them, and you do a one sample t-test. You could also do something kind of cool, which is give everybody, because this experiment is blind, because you can't tell what the treatment is. Then what you could do is you could randomly give everybody either a left boot that has one method and the right boot with the other, and then just randomly assign them across the 100 people, and then just measure the wear, and then plot that as a one sample t-test. Okay. I kind of went through that pretty quick, but I do want to, like if you're hoping to go to the opening ceremonies and want to impinge on that too much, thank you guys for coming. It was a great turnout today. I'm really excited that you guys are prepping hard for the AP Stat exam. Stat is such a great skill to take with you, if nothing else. But this exam is totally in your power. We're very fond of saying here, all your exams are 5-able, especially this one.